Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Tonight we're going to drift together through the most soothing truths about our universe. Gentle facts that will cradle your mind as you slip towards sleep. There's nothing you need to do now except breathe slowly. Let your thoughts grow soft and allow yourself to be carried along by the quiet wonders we'll explore. We'll move gently from one cosmic truth to another, learning about distant worlds, ancient light, and the beautiful rhythms that govern everything from the smallest particles to the largest structures in space. If these calm explorations help you find rest or spark a quiet curiosity that carries you into dreams, please consider liking and subscribing to the channel. The universe hums with a gentle background song that has been playing for billions of years. Deep in space, there exists a quiet melody that most of us will never hear, but it's always there, like the distant sound of wind through trees. This cosmic background radiation fills every corner of the universe, a soft whisper left over from the very beginning of time. It's not loud or jarring, just a peaceful murmur that bathes everything in existence. When scientists first detected this ancient song, they described it as the universe's lullaby, a gentle reminder that even in the vastness of space, there is something warm and constant surrounding us all. Somewhere in the depths of space, there are clouds made entirely of water vapor that dwarf our entire solar system. These cosmic clouds drift silently through the darkness, containing more water than all the oceans on Earth combined. They float like gentle giants, invisible to our eyes but detected by sensitive instruments that can sense their presence across the light years. Some of these water clouds are warm, heated by nearby stars, creating vast regions of cosmic steam that would feel almost tropical if you could somehow visit them. Others are cold and serene, their molecules moving slowly in the chill of deep space, like morning mist frozen in time. The light from some stars takes so long to reach us that when we see them twinkling in the night sky, we're actually looking into the distant past. A star that appears to shine brightly tonight might have gone out centuries ago, but its light continues traveling toward us across the cosmic ocean, carrying the memory of its glow. This means that every time you look up at the stars, you're seeing a collection of different moments in time, all gathered together in the present sky. It's as if the universe keeps a gentle archive of light, preserving the beauty of distant suns long after they've found their rest. In the cold regions between stars, there are vast libraries of frozen molecules, including the building blocks of life itself. These cosmic deep freezers contain water, alcohol, sugar, and even more complex organic compounds, all preserved in the near absolute zero of space. They drift quietly through the galaxy like seeds waiting for the right moment to bloom into something new. When these molecular clouds eventually collapse to form new stars and planets, they carry with them the ingredients for oceans, atmospheres, and perhaps even life. It's a beautiful thought that the universe has been preparing the recipe for existence long before any particular world was ready to receive it. Some planets in distant solar systems rain diamonds from their skies. On worlds where the atmospheric pressure and chemistry are just right, carbon in the air can be compressed and heated until it crystallizes into tiny gems. These diamond raindrops fall gently through alien atmospheres, creating shimmering cascades that would dazzle anyone fortunate enough to witness them. The diamonds eventually settle into vast deposits on the planet's surface, turning entire landscapes into glittering fields of precious stones. These worlds exist far beyond our reach, but knowing they're out there adds a touch of magic to the night sky. There are moons in our solar system that have more water than all of Earth's oceans combined. Beneath the frozen surfaces of distant moons like Europa and Enceladus lie vast underground seas, kept liquid by the gentle tidal heating from their parent planets. These hidden oceans are dark and peaceful, protected from the harsh environment of space by thick layers of ice. In these quiet depths, warmed by geological forces, conditions might be just right for life to flourish in ways we can barely imagine. The idea that there are entire worlds of possibility hidden beneath what appears to be barren ice is both humbling and comforting. The universe is filled with invisible rivers of dark matter that flow gently between galaxies. These cosmic currents are made of mysterious particles that don't interact with light, making them impossible to see directly. But their presence can be felt through their gravitational influence, like sensing the wind by watching leaves dance. These dark matter streams connect distant galaxies in a vast web, creating a hidden network that spans the entire observable universe. It's as if the cosmos has its own circulatory system, quietly moving unseen materials from one region to another in a dance that has been going on since the beginning of time. Some stars pulse with the regularity of cosmic heartbeats, brightening and dimming in perfect rhythm. These variable stars expand and contract like breathing, creating gentle waves of light that travel across space. Astronomers use these stellar heartbeats to measure distances to far-off galaxies, turning the natural rhythms of the universe into tools for exploration. The most reliable of these stellar timekeepers are so precise that they rival the best clocks ever built by human hands. In their steady pulsing, we find a sense of cosmic order and reliability that transcends the chaos of everyday life. There are regions of space where time itself moves more slowly than it does on Earth. Near massive objects like black holes, the fabric of space-time becomes curved and stretched, causing clocks to tick more leisurely. This isn't science fiction, but a gentle consequence of how gravity shapes the universe around us. If you could somehow visit these regions, you would age more slowly compared to someone back on Earth, experiencing time like honey flowing instead of water rushing. This cosmic time dilation means that the universe contains pockets of temporal peace, places where the hurried pace of existence naturally slows down. In the depths of space, there are giant soap bubbles made of glowing gas, blown by the breath of dying stars. These cosmic bubbles can be dozens of light years across, their delicate walls shimmering with the colors of heated atoms. They expand slowly and gracefully, like bubbles blown by a cosmic child, carrying the enriched materials of stellar death to fertilize future generations of stars and planets. When we observe these nebulae through telescopes, we see them as some of the most beautiful objects in the universe, their soft curves and gentle colors creating natural art on an impossible scale. The space between planets in our solar system isn't truly empty. but is filled with a gentle wind of particles flowing from our sun. This solar wind carries charged particles across billions of miles, creating a vast sphere of influence around our star. When these particles interact with planetary magnetic fields, they create beautiful displays of light called auroras, painting the night skies of distant worlds with curtains of green, blue, and red. Even on Earth, this solar wind gives us the northern and southern lights, a regular reminder of the sun's gentle touch, reaching across the void to embrace our planet. There are ancient galaxies whose light has been traveling toward us since before our solar system even existed. When we peer deep into space with our most powerful telescopes, we can see these primordial islands of stars as they appeared when the universe was young and chaotic. These early galaxies were smaller and more irregular than the grand spirals we see today, but they held the seeds of everything that would come after. Observing them is like reading the universe's childhood diary, filled with the innocent experiments of cosmic youth before the mature structures we know today had time to develop. Some comets carry water that is older than our sun, ice that formed in the coldest regions of space before our solar system was even a possibility. When these ancient ice balls visit the inner solar system, they release this primordial water as vapor, creating the beautiful tails that stream behind them like cosmic veils. This water contains the memory of interstellar space, preserving the conditions that existed between the stars billions of years ago. The fact that such ancient materials still exist and occasionally visit our neighborhood adds a sense of deep continuity to our place in the cosmos. In certain regions of space, magnetic fields create vast loops and spirals that channel the flow of cosmic particles like invisible highways. These magnetic structures can span hundreds of light years, guiding charged particles along graceful curves that would be impossible to see with ordinary light. The particles follow these magnetic roads at tremendous speeds, but their motion is smooth and orderly, creating cosmic currents that help shape the larger structure of galaxies. It's as if the universe has its own transportation network, moving materials and energy along routes that have been established over millions of years. There are planets that orbit their stars in such perfect synchronization that they always show the same face to their sun, just as our moon does to Earth. On these tidally locked worlds, one side experiences eternal day while the other knows only night, creating a permanent twilight zone where the temperature is just right for liquid water. These twilight regions might be the most peaceful places in the universe, where the harsh extremes of scorching heat and freezing cold give way to a gentle, perpetual sunset. The idea that such serene cosmic oases exist somewhere among the stars is deeply comforting. Some asteroids tumble through space in complex rotations that create natural works of kinetic art. As they spin and tumble, these space rocks catch and reflect sunlight in ever-changing patterns, creating light shows that no human eye has ever witnessed. Their surfaces, scarred by billions of years of cosmic collisions, tell stories of the solar system's violent youth, but their current gentle dance through the void speaks of the peace that comes after the storm. These solitary performers continue their cosmic ballet far from any audience, finding beauty in motion for its own sake. The universe contains vast networks of cosmic strings, theoretical structures so thin they would be invisible even if they passed right through you, yet so dense that a single inch would weigh more than Mount Everest. These cosmic strings, if they exist, would stretch across enormous distances, creating a web of almost incomprehensible delicacy and strength. They would vibrate like guitar strings when disturbed, potentially creating gravitational waves that could be detected by sensitive instruments. The possibility that space itself might be threaded with these invisible fibers adds another layer of hidden beauty to the cosmic tapestry. There are neutron stars that spin so rapidly they create their own music, sending out beams of radio waves like cosmic lighthouses that sweep across space hundreds of times per second. These stellar remnants, no larger than a city but containing more mass than our sun, rotate with such precision that their pulses can be timed more accurately than the finest atomic clocks. As these beams wash over Earth in their endless rotation, they create rhythmic patterns that scientists have learned to interpret like reading sheet music, written in the language of collapsed stars. Each pulsar has its own signature tempo, contributing to a vast cosmic symphony that plays continuously in frequencies we cannot hear but can detect and appreciate. In the outer reaches of our solar system, there exists a spherical cloud of icy bodies called the Oort cloud, a vast and peaceful reservoir of potential comets that extends nearly halfway to the nearest star. This cosmic nursery contains billions of frozen remnants from the formation of our solar system, each one a pristine time capsule, preserving the conditions that existed when the planets were young. Most of these icy wanderers will never venture close to the sun, content to drift in the cold darkness at the very edge of our star's influence. Occasionally, a gentle gravitational nudge from a passing star will send one of these sleeping giants on a long journey toward the inner solar system, where it will bloom into a magnificent comet, its tail streaming behind it like a banner of ancient ice and dust. The aurora displays that paint Earth's polar skies are just one small part of a much grander phenomenon that occurs throughout the solar system. Jupiter's moons experience auroras far more intense and colorful than anything we see on Earth, with curtains of light that dance across alien skies in shades of blue, green, and ultraviolet. Saturn's rings themselves glow with a subtle aurora, creating a faint luminescence that adds to the planet's ethereal beauty. Even distant Uranus and Neptune host their own versions of these light shows, proving that the interaction between solar wind and magnetic fields creates beauty wherever the right conditions exist. Deep space contains vast molecular clouds where the temperature hovers just a few degrees above absolute zero, creating natural laboratories where chemistry unfolds at an almost meditative pace. In these frigid environments, atoms and molecules move so slowly that reactions that would be explosive under normal conditions proceed with gentle deliberation. Complex organic molecules form gradually over millions of years, building up layer by layer like cosmic sediment. Some of these clouds are so large they could contain thousands of solar systems, yet they are so diffuse that you could fly through them without noticing, surrounded by the raw materials of future worlds dissolving invisibly around you. There are binary star systems where two suns dance around each other in gravitational embrace, their mutual orbits so perfectly balanced that they have been waltzing through space for billions of years. Some of these stellar pairs are so close, they exchange material in graceful streams of hot gas, while others maintain a respectful distance, content to share the same cosmic neighborhood without touching. On planets that orbit such systems, inhabitants would witness double sunrises and sunsets, with two shadows cast by every object and a sky that never experiences true darkness, as long as both stars remain above the horizon. The space around Earth is filled with a protective magnetic field that acts like an invisible shield, deflecting harmful cosmic radiation and charged particles from the solar wind. This magnetosphere extends far beyond our atmosphere, creating a bubble of safety that has allowed life to flourish on our planet's surface. When this magnetic field interacts with incoming solar particles, it guides them toward the poles, where they create the beautiful aurora displays that have inspired humans throughout history. Without this gentle magnetic embrace, Earth's atmosphere might have been stripped away long ago, leaving our world as barren as Mars. In the center of our galaxy lies a supermassive black hole that, despite its fearsome reputation, currently rests in a state of relative quiet. This cosmic giant, millions of times more massive than our Sun, sits peacefully at the galactic core, only occasionally stirring when gas or stars venture too close to its event horizon. Most of the time, it simply exists as a gravitational anchor around which hundreds of billions of stars orbit in their slow, stately dance. The fact that such an immense object can remain so tranquil for millions of years at a time speaks to the universe's capacity for both power and patience. Some of the water on Earth arrived via comets and asteroids billions of years ago, meaning that every glass of water you drink contains molecules that once drifted freely through interstellar space. These cosmic travelers carried with them the memory of distant molecular clouds, preserving the chemical signatures of regions far beyond our solar system. When you look out at the night sky and then take a sip of water, you're participating in a connection that spans both space and time, linking your body to the vast network of material exchange that has been going on since the universe began forming its first stars and planets. There are rogue planets that wander through interstellar space without orbiting any star. Dark worlds that travel alone through the cosmic night. These planetary nomads were either ejected from their birth systems by gravitational interactions or formed independently in the cold depths between stars. Despite having no sun to warm them, some of these worlds might still harbor life, sustained by the heat generated by radioactive decay in their cores, or by tidal heating from large moons. The possibility that entire ecosystems might exist in the darkness between stars, completely independent of stellar light, adds a mysterious beauty to the empty spaces of the galaxy. The cosmic web that connects galaxies across the universe resembles a vast neural network, with filaments of dark matter and gas creating bridges between distant island universes. Along these cosmic highways, matter flows slowly from one region to another, carrying the building blocks of stars and planets across distances so vast that the journey takes billions of years to complete. At the intersections of these filaments, galaxies cluster together like cities connected by invisible roads. sharing materials and gravitational influence in a grand network that spans the entire observable universe. Some stars are so old, they formed when the universe contained almost no heavy elements, making them living fossils from cosmic antiquity. These ancient suns burn with a pure light that carries the chemical signature of a much simpler time, when only hydrogen and helium existed in significant quantities. They drift through the galaxy like elderly wanderers, their slow orbits carrying them far above and below the main disk, where younger stars like our sun reside. Studying these stellar ancients gives us a window into the universe's childhood, when the first generation of stars was just beginning to forge the elements that would eventually make planets and life possible. The magnetosphere of Jupiter is so enormous, it would be visible from Earth if we could see magnetic fields with our naked eyes, appearing larger than the full moon in our night sky. This giant magnetic bubble traps charged particles from the solar wind, creating radiation belts far more intense than Earth's Van Allen belts. Within this magnetic cocoon, Jupiter's moons orbit like ships sailing through an invisible ocean of electromagnetic forces, some experiencing radiation levels that would be lethal to unprotected life, while others remain sheltered in magnetic shadows, where conditions are more benign. There are white dwarf stars that have crystallized into cosmic diamonds, their carbon and oxygen cores compressed and cooled over billions of years until they form the largest gemstones in the universe. These stellar diamonds are about the size of Earth, but contain roughly half the mass of our Sun, creating gravitational fields so intense that a sugar cube of their material would weigh as much as an automobile. As they continue to cool over trillions of years, these cosmic jewels will eventually become cold, dark crystals drifting silently through space, beautiful beyond imagination, but invisible to any observer except through their gravitational influence on nearby objects. The heliopause, the boundary where our sun's influence gives way to interstellar space, is not a sharp edge, but a gentle transition zone where the solar wind gradually mingles with the cosmic medium between stars. Both Voyager spacecraft have crossed this boundary, becoming humanity's first ambassadors to interstellar space, carrying with them golden records containing sounds and images from Earth. In this quiet frontier region, the familiar environment of our solar system slowly fades into the larger galactic community, marking a boundary that is both an ending and a beginning, a place where our cosmic neighborhood opens into the vast unknown. Some galaxies rotate so slowly that a single spin takes hundreds of millions of years to complete, creating cosmic carousels that turn with the patience of geological time. These gentle giants drift through space like vast pinwheels caught in an eternal breeze, their spiral arms maintaining their graceful curves across eons. Stars born on one side of these galaxies will complete entire life cycles before they reach the other side, making the galaxy's rotation a journey that spans generations of stellar evolution. The leisurely pace of these cosmic dancers reminds us that the universe operates on timescales so vast that even the most dramatic changes unfold with serene deliberation. In the depths of space, there are regions where gravity is so weak that a gentle push could send you drifting for millions of miles without ever slowing down. These cosmic doldrums exist at the gravitational balance points between massive objects, creating pockets of near weightlessness that extend across vast distances. Spacecraft visiting these regions experience a profound sense of floating, suspended in a three-dimensional ocean where up and down lose all meaning. The silence and stillness of these gravitational oases provide a natural sanctuary from the constant pull and tug of planetary and stellar forces. There are ancient photons of light that have been bouncing around inside certain stars for millions of years before finally escaping to begin their journey through space. Deep within stellar cores, where nuclear fusion creates new light every second, the intense density means that each photon must zigzag through countless collisions with atoms, taking a random walk that can last geological ages. By the time this light finally reaches the star's surface and streams out into space, it carries with it the memory of an incredibly long and patient journey through the star's interior, making even the youngest starlight surprisingly ancient. Some moons in our solar system have such weak gravity that you could achieve orbital velocity simply by throwing a baseball with a good strong arm. On these tiny worlds, the escape velocity is so low that dust kicked up by micrometeorite impacts can drift away into space, never to return. Walking on the surface of such a moon would feel more like floating through a dream, where each step could potentially launch you into a gentle arc that might last for minutes before you slowly settle back to the ground. The delicate gravitational embrace of these small worlds creates environments where motion becomes poetry. Deep in the cosmic web, there are vast bubbles of almost empty space called cosmic voids, regions so devoid of matter that a journey across one would take hundreds of millions of years at the speed of light. These cosmic deserts contain almost no galaxies, just the occasional lonely star or wandering gas cloud drifting through the darkness. Within these voids, the universe reveals its capacity for profound emptiness, creating cathedrals of space so large that entire galactic superclusters could fit within them, with room to spare. The peace and solitude of these regions is absolute, representing the universe's most perfect meditation halls. There are stellar nurseries where new stars are born so gently that the process unfolds like a cosmic slow-motion ballet. In these molecular clouds, gravity works with infinite patience, gradually gathering material over millions of years until the accumulating mass reaches the critical point where nuclear fusion ignites. The birth of each new star sends ripples through the surrounding gas, triggering the formation of siblings and companions in a chain reaction of creation that spreads throughout the cloud. These stellar maternity wards glow with the soft light of protostars, cosmic cocoons where the universe nurtures its newest lights. Some asteroids have such low density that they're essentially flying rubble piles held together by the gentlest gravitational touch. These cosmic loose collections drift through space like three-dimensional puzzles that could be taken apart by a strong sneeze. Yet they maintain their coherent shape across millions of years of travel. When spacecraft visit these fragile worlds, they must approach with extreme caution, as their exhaust could literally blow the asteroid apart. The delicate balance that keeps these rubble piles intact speaks to the subtle forces that govern motion and structure throughout the solar system. In certain nebulae, the pressure of starlight is strong enough to sculpt gas and dust into intricate shapes, creating cosmic topiary gardens carved by photons. The radiation from hot young stars pushes against surrounding material with gentle but persistent force, slowly molding the interstellar medium into pillars, caverns, and flowing streams of luminous gas. These stellar winds work like invisible hands shaping clay, taking millions of years to complete their artistic vision. The resulting structures often resemble earthly formations like mountains, canyons, or ocean waves, as if the universe follows similar aesthetic principles regardless of scale. There are binary star systems where the two stars are so perfectly matched that they orbit their common center with clockwork precision, neither gaining nor losing energy over billions of years. These stellar partners maintain their cosmic dance with such accuracy that they can be used as natural timekeepers, their orbital periods remaining constant to within fractions of a second over geological ages. The gravitational harmony between these paired suns creates a stability that rivals the finest mechanical chronometers ever built, turning regions of space into vast clockwork mechanisms governed by the mathematics of orbital motion. Some comets follow such elongated orbits that they spend most of their existence in the cold outer reaches of the solar system, only rarely swooping close to the sun for brief moments of glory. These cosmic wanderers spend centuries or millennia in frozen hibernation, their surfaces unchanged by the passage of time. When they finally approach the inner solar system, the sun's heat awakens them from their long sleep, causing their icy cores to sublime into glorious tails that can stretch for millions of miles. After this brief display, they retreat once again to the cold darkness, carrying with them the memory of their solar encounter. The space between galaxies is filled with a tenuous medium of hydrogen gas, so thin that it contains only a few atoms per cubic meter. Yet this near vacuum still plays a crucial role in cosmic evolution. This intergalactic medium serves as a reservoir of raw material that can be drawn into galaxies to fuel new generations of star formation. The gas moves slowly through space, following the gravitational currents created by the cosmic web, participating in a grand circulation system that connects even the most distant galaxies. Its extreme thinness makes it almost undetectable, yet its presence ensures that the universe remains a dynamic, evolving system rather than a collection of isolated islands. There are planets where the atmospheric pressure is so low that water would instantly boil away, yet the temperatures are so cold that the vapor would immediately freeze into snow, creating worlds where it simultaneously snows and boils. These paradoxical environments exist at the edges of stellar habitable zones, where the delicate balance between heat and cold creates conditions unlike anything found on Earth. On such worlds, weather systems would operate according to alien physics, with storms of sublimating ice and precipitation that changes phase in mid-fall. Some galaxies are connected by bridges of stars and gas that stretch across hundreds of thousands of light years, creating cosmic architecture on scales that dwarf any earthly construction. These tidal streams form when galaxies pass close enough to each other that their mutual gravitational attraction pulls material from one system to another. The resulting stellar bridges can persist for hundreds of millions of years, serving as highways along which stars migrate between galactic neighborhoods. These connections remind us that even on cosmic scales, no structure exists in complete isolation. In the cores of certain planets, the pressure is so intense that ordinary matter takes on exotic properties, with hydrogen becoming metallic and conducting electricity like copper wire. These high-pressure laboratories exist naturally in the depths of gas giants, creating conditions that scientists can barely reproduce in earthly experiments. The metallic hydrogen cores of planets like Jupiter generate powerful magnetic fields that extend far into space, creating protective bubbles that shield their moons from harmful radiation. These planetary dynamos demonstrate how extreme conditions can give rise to protective systems that nurture more delicate environments. There are star clusters so old and stable that they have maintained their gravitational cohesion since the early days of the galaxy, serving as time capsules that preserve samples of ancient stellar populations. These globular clusters orbit high above the galactic disk, following paths that carry them through regions of space largely unchanged since their formation. Within these stellar communities, hundreds of thousands of stars have lived together for billions of years, creating gravitational neighborhoods where stellar interactions unfold over timescales longer than the age of complex life on Earth. Some neutron stars have magnetic fields so powerful they could erase every credit card on Earth from a distance of thousands of miles. Yet these cosmic magnets spin with such regularity that they make perfect clocks. The combination of extreme magnetism and precise rotation creates natural lighthouses that sweep beams of radiation across space with metronomic accuracy. These stellar timekeepers are so reliable that astronomers use them to detect the subtle stretching of space caused by gravitational waves from distant cosmic collisions. In certain regions of space, the cosmic microwave background radiation has been focused and amplified by gravitational lensing, creating natural telescopes that allow us to peer deeper into the universe's past than should otherwise be possible. These cosmic magnifying glasses are formed when massive galaxy clusters bend space-time, concentrating the ancient light that has been traveling toward us since shortly after the Big Bang. Through these gravitational lenses, we can observe galaxies that formed when the universe was just a fraction of its current age, witnessing cosmic dawn through nature's own optical instruments. There are molecular clouds in space that contain enough alcohol to fill every ocean on Earth, drift in through the galaxy like cosmic distilleries operating on interstellar scales. These clouds form complex organic molecules through slow chemical processes that unfold over millions of years, creating reservoirs of prebiotic chemistry in the cold depths between stars. When these clouds eventually collapse to form new solar systems, they seed the resulting planets with the chemical building block that might one day give rise to life. Some exoplanets orbit so close to their parent stars that their surfaces are completely molten, creating worlds of eternal lava oceans beneath skies filled with vaporized rock. Despite their hellish conditions, these planets serve as natural laboratories for studying extreme geology and atmospheric dynamics. The constant volcanic activity on these worlds creates weather systems made of silicate clouds and metal rain. demonstrating how familiar processes can create utterly alien environments when pushed to their limits. Deep space contains vast magnetic structures that channel cosmic rays along invisible highways, guiding these high-energy particles on journeys that can span the entire galaxy. These magnetic fields, generated by the collective motion of charged particles throughout space, create a hidden infrastructure that influences the flow of energy and matter on cosmic scales. The paths followed by cosmic rays reveal the presence of these magnetic roadways, mapping out a transportation network that connects distant regions of the galaxy through electromagnetic forces. There are ancient white dwarf stars that have been cooling for so long. They have formed crystalline cores of pure carbon and oxygen, creating cosmic gemstones that will continue to exist long after all the normal stars have burned out. These stellar diamonds represent the final fate of stars like our Sun, transformed through billions of years of cooling into objects of perfect crystalline beauty. They will persist as monuments to stellar evolution, shining faintly with residual heat as the universe grows cold and dark around them. In the furthest reaches of our solar system, there are regions where the Sun appears as nothing more than a bright star, no different from the thousands of others scattered across the night sky. Here, in the realm of the Kuiper Belt and beyond, sunlight is so faint that high noon resembles a perpetual twilight, creating landscapes bathed in the soft glow of distant starlight. On these frozen worlds, shadows are gentle and diffuse, cast by the combined light of countless stars, rather than a single dominant sun. The silence in these outer territories is profound, broken only by the occasional whisper of solar wind carrying messages from the warm inner planets billions of miles away. Some galaxies move through space like cosmic jellyfish, their trailing streams of stars and gas flowing behind them as they drift through the intergalactic medium. These ram-pressure-stripped galaxies lose material as they travel, creating beautiful tails that can stretch for hundreds of thousands of light years. The stars within these tails continue to shine as they are slowly pulled away from their parent galaxy, forming temporary stellar streams that gradually disperse into the cosmic background. This gentle process of galactic erosion happens so slowly that individual stars barely notice their changing allegiance, continuing their nuclear fusion as they transition from one gravitational family to another. Deep within certain asteroids, there are caverns filled with perfect vacuum, creating natural chambers where nothing exists except empty space and the faint gravitational pull of surrounding rock. These cosmic caves formed billions of years ago when the asteroids were still molten, gas bubbles becoming trapped and preserved as the material cooled and solidified. Today, these hidden voids drift silently through space, containing pockets of nothingness more perfect than any vacuum we can create in earthly laboratories. If you could somehow visit one of these chambers, you would experience the purest form of stillness, surrounded by rock but floating in absolute emptiness. There are brown dwarf stars that never quite managed to ignite nuclear fusion, existing in a peaceful state between planet and star that astronomers call failed suns. These cosmic in-betweens glow faintly with leftover heat from their formation, slowly cooling over billions of years like embers from a fire that never quite caught. They drift through space in solitary meditation, too massive to be planets, but too small to be stars, occupying their own quiet category of celestial existence. Some of these brown dwarfs have weather systems with clouds made of liquid iron and silicate rain, creating atmospheric dynamics unlike anything found on conventional planets. In certain spiral galaxies, the rotation is so perfectly organized that density waves sweep through the spiral arms like slow-motion tsunamis made of stars and gas. These galactic waves trigger star formation as they pass, lighting up the spiral structure in a pattern that rotates more slowly than the individual stars themselves. The result is a cosmic light show that unfolds over millions of years, with bright young stars marking the wave's passage like phosphorescence in a cosmic ocean. This stellar choreography creates the beautiful spiral patterns we observe in distant galaxies, each one a slow-motion firework frozen in the act of perpetual blooming. Some moons in our solar system are tidally heated by the gravitational massage of their parent planets, creating warm underground oceans beneath icy surfaces that never see direct sunlight. This gentle kneading action, caused by the changing strength of gravitational pull as the moons follow slightly elliptical orbits, generates enough heat to keep vast bodies of water liquid in regions where temperatures would otherwise freeze everything solid. These hidden seas may be some of the most stable environments in the solar system, protected from temperature fluctuations and radiation by their icy shells, creating cosmic aquariums that have remained unchanged for millions of years. There are regions of space where the cosmic microwave background radiation has been stretched and cooled by the expansion of the universe to the point where it barely registers above absolute zero. In these cosmic refrigerators, matter moves with glacial slowness, and chemical reactions that would be instantaneous under normal conditions take millennia to complete. These ultra-cold regions serve as natural laboratories for studying quantum effects on macroscopic scales, where the wave-like properties of matter become apparent, and the boundary between particles and waves dissolves into quantum uncertainty. Some binary star systems are so close together that they share a common atmosphere, creating stellar partnerships where the boundary between one star and another becomes beautifully blurred. These contact binaries rotate around each other so rapidly that their mutual gravitational pull stretches them into egg-shaped forms, with streams of hot gas flowing between them in graceful arcs. The two stars in such systems can exchange mass and energy, sometimes causing one to grow while the other shrinks, creating a slow-motion stellar dance that plays out over millions of years. In the depths of molecular clouds, there are regions where magnetic fields have twisted into complex knots and loops, creating invisible sculptures that guide the formation of new stars. These magnetic structures can persist for millions of years, slowly evolving as they interact with turbulent gas flows and gravitational collapse. The resulting magnetic topologies are often more intricate than any human artwork, with field lines that spiral, braid, and reconnect in patterns of stunning mathematical beauty. When star formation finally begins within these clouds, the new protostars follow the magnetic architecture, creating stellar nurseries organized according to invisible blueprints. written in electromagnetic force. There are comets whose orbits are so perfectly aligned with the plane of the solar system that they appear to follow the same path year after year, like cosmic trains running on invisible rails. These periodic visitors return with clockwork precision. Their appearances predicted centuries in advance by astronomers who have mapped their gravitational trajectories through space. Between visits, they sleep in the cold outer darkness, their surfaces unchanged by the passage of time, waiting patiently for their next appointment with the sun. When they finally return, they bring with them ice and dust that may be older than the Earth itself, delivering samples of the primordial solar system to our cosmic doorstep. Some planets have such thick atmospheres that the surface pressure would crush any earthly visitor. Yet these same dense envelopes create greenhouse effects so powerful that they maintain tropical temperatures even at distances where water would normally freeze solid. These super greenhouse worlds demonstrate how atmospheric composition can completely override the simple relationship between distance from a star and surface temperature. On such planets, weather systems operate under extreme pressure, creating wind patterns and storm systems that dwarf anything found on Earth, while maintaining surface conditions that remain remarkably stable over geological time. In certain globular star clusters, the gravitational interactions between hundreds of thousands of stars have created a perfect balance that has persisted for billions of years. These stellar communities are so stable that they serve as cosmic time capsules, preserving samples of the galaxy's earliest stellar populations in pristine condition. The stars within these clusters have grown old together, their evolution synchronized by their shared gravitational environment. Some clusters are so tightly bound that they have survived multiple passages through the galactic disk, maintaining their integrity despite gravitational tides that would tear apart less cohesive stellar groups. There are nebulae where the interplay between stellar radiation and cosmic dust creates optical effects that change depending on the viewing angle, making these cosmic clouds appear different to observers in different parts of the galaxy. These perspective-dependent phenomena result from the way light scatters off microscopic dust grains, creating colors and patterns that shift and change like cosmic kaleidoscopes. What appears as a brilliant emission nebula to one observer might look like a dark absorption cloud to another, demonstrating how cosmic beauty is often a matter of perspective and position. Some asteroid families are the scattered remnants of ancient collisions, their members following similar orbits that reveal their common origin billions of years after the impact that created them. These cosmic archaeology sites preserve evidence of catastrophic events from the solar system's violent youth, when planetary formation was still in progress and collisions were common. The fragments continue to follow orbital paths that bear the signature of their shared trauma, creating groups of asteroids that serve as witnesses to ancient cosmic violence that has long since given way to the peaceful dynamics we observe today. Deep in the hearts of certain planets, the pressure and temperature conditions create exotic forms of matter that exist nowhere else in the solar system. These high-pressure laboratories produce materials with properties that seem almost magical, such as metallic hydrogen that conducts electricity better than copper, or supersonic ice that flows like liquid while maintaining a crystalline structure. These extreme states of matter play crucial roles in generating the magnetic fields and internal heat sources that make planets geologically active and capable of supporting complex atmospheric dynamics. There are stellar remnants called magnetars that possess magnetic fields so intense they warp the very atoms in their vicinity, creating regions where the normal rules of chemistry and physics break down completely. These cosmic magnets are so powerful that they can strip electrons from atoms at distances of thousands of miles, yet they rotate with such perfect regularity that they serve as the most precise clocks in the universe. The combination of extreme magnetism and perfect timing creates natural phenomena that stretch our understanding of how matter and energy behave under the most extreme conditions imaginable. In certain regions of the cosmic web, dark matter filaments have become so concentrated that they act like gravitational lenses, focusing and magnifying light from distant galaxies in ways that create natural telescopes spanning millions of light years. These cosmic magnifying glasses allow us to observe galaxies that would otherwise be too faint and distant to detect, effectively extending our vision deeper into space and further back in time. The dark matter that creates these lenses remains invisible, but its presence is revealed through the distorted and amplified images of the galaxies behind it. Some exoplanets have been discovered with retrograde orbits, traveling around their stars in the opposite direction from the planet's rotation during formation. These backwards worlds challenge our understanding of planetary system evolution, suggesting that gravitational interactions can completely reverse a planet's orbital motion over time. The mechanisms that create these retrograde planets involve complex multi-body dynamics that can flip orbits through a series of gravitational encounters, demonstrating how chaotic the process of planetary system evolution can be. There are regions in space where multiple gravitational influences create Lagrange points, cosmic parking spaces where a small object can remain stationary relative to larger bodies without using any fuel. These gravitational balance points exist wherever two massive objects create a stable configuration, providing natural harbors in the cosmic ocean where spacecraft can loiter indefinitely. Some of these points collect dust and small asteroids over millions of years, creating natural accumulations of material that follow the same orbital path as planets, while remaining gravitationally distinct. In the outer atmospheres of certain gas giants, there are jet streams that circle the planet at speeds exceeding the fastest winds ever recorded on Earth. Yet these atmospheric rivers maintain their coherent structure for decades or centuries without breaking up. These persistent wind patterns are driven by the planet's internal heat and rapid rotation, creating weather systems that dwarf terrestrial storms in both size and longevity. The mathematical beauty of these atmospheric flows demonstrates how simple physical principles can give rise to complex, self-organizing patterns that persist across geological timescales. Some white dwarf stars have companion objects that orbit so closely they complete a full revolution in less than an hour, creating binary systems where orbital mechanics operates at breakneck speed compared to planetary motion. These ultra-compact binaries are often composed of exotic objects like neutron stars or other white dwarfs, creating gravitational laboratories where Einstein's theories of relativity can be tested under the most extreme conditions. The orbital decay of these systems due to gravitational wave emission provides direct evidence for one of the most subtle predictions of general relativity. There are molecular clouds in space that contain organic molecules complex enough to be considered the building blocks of life. Yet these cosmic chemistry sets operate at temperatures so cold that reactions proceed millions of times more slowly than they would under earthly conditions. These interstellar laboratories demonstrate that the universe naturally produces the chemical precursors necessary for biology, suggesting that the ingredients for life may be distributed throughout the galaxy in vast molecular reservoirs, waiting for the right conditions to come together. In certain binary star systems, the transfer of mass from one star to another creates spectacular displays of cosmic fireworks, with nova explosions that can temporarily increase the system's brightness by factors of thousands or millions. These stellar tandem acts involve one star gradually stealing material from its companion, building up layers of hydrogen on its surface until the accumulated fuel ignites in a thermonuclear flash. After the explosion, the cycle begins again, creating periodic displays that can repeat over timescales ranging from years to centuries. Some galaxies have been observed in the process of forming tidal tails, long streams of stars and gas that stretch across hundreds of thousands of light years as gravitational forces slowly pull them apart. These galactic disruption events unfold over hundreds of millions of years, creating some of the most beautiful and ephemeral structures in the universe. The stars within these tidal streams continue to shine normally, even as they are separated from their parent galaxy, creating temporary stellar rivers that eventually disperse into the intergalactic medium. There are neutron stars that spin so rapidly they approach the theoretical limit where centrifugal force would overcome gravity, creating objects that exist on the very edge of physical possibility. These millisecond pulsars rotate hundreds of times per second while maintaining perfect spherical symmetry, demonstrating how extreme gravitational fields can maintain structural integrity under conditions that would tear apart any normal matter. The precision of their rotation makes them natural cosmic chronometers more accurate than any clock ever built by human technology. Deep in the cores of certain asteroids, scientists have discovered that the intense pressure created during formation has produced materials with properties unlike anything found on Earth's surface. These high-pressure minerals preserve records of the violent conditions that existed during the solar system's early formation, when collisions were frequent and energetic enough to create exotic crystal structures. Studying these materials provides insights into the processes that shaped the planets and moons we observe today. In some regions of space, the interaction between cosmic ray particles and magnetic fields creates vast acceleration zones, where particles are boosted to energies far exceeding anything achievable in earthly laboratories. These natural particle accelerators operate continuously, powered by the rotation of neutron stars or the accretion of matter onto black holes. The resulting high-energy particles travel throughout the galaxy, carrying information about the extreme environments where they originated and providing a continuous background of cosmic radiation that bathes all of space. There are ancient photons that have been traveling through space for so long that they began their journey when the universe was a fraction of its current size, carrying with them the memory of a cosmos that was denser, hotter, and filled with structures that no longer exist. These messenger particles have witnessed the entire history of cosmic evolution, passing through regions where galaxies were just beginning to form and continuing their patient journey as those same galaxies matured, merged, and sometimes faded away. When these ancient photons finally reach our telescopes, they deliver news from epochs so distant that the light itself has been stretched and reddened by the expansion of space, transforming what were once high-energy signals into gentle whispers of electromagnetic radiation. Some planetary rings are so thin that if you could scale them down to the size of a piece of paper, they would be thousands of times thinner than that sheet. Yet they maintain their structure across distances that span tens of thousands of miles. These gossamer bands of ice and rock particles orbit their parent planets in perfect formation, held in place by the delicate balance between gravitational forces and orbital mechanics. The particles within these rings range in size from dust grains to house-sized boulders, all following their own individual orbits, while contributing to the collective beauty of the ring system. Shepherd moons patrol the edges of these rings, their gravitational influence keeping the particles confined to narrow bands that can persist for millions of years. In certain stellar nurseries, the process of star formation creates feedback loops where the radiation from newly born stars triggers the collapse of nearby gas clouds, which in turn form additional stars that repeat the process. These stellar chain reactions can propagate across entire molecular clouds over millions of years, creating waves of star formation that sweep through galactic regions like slow-motion fires spreading through cosmic forests. The resulting stellar associations contain stars of similar ages that share common motion through space, creating extended families of suns that were born from the same primordial material and continue to travel together long after their birth clouds have dissipated. There are cosmic structures called dark matter halos that extend far beyond the visible boundaries of galaxies, creating invisible scaffolding that determines how galaxies move and interact with each other. These dark matter envelopes can be 10 times larger than the galaxy they surround, yet they remain completely undetectable except through their gravitational influence on visible matter. The intricate architecture of these halos has been sculpted over billions of years by cosmic collisions and mergers, creating complex substructures and streams that tell the story of how galaxies assembled from smaller components scattered throughout the early universe. Some binary asteroid systems orbit each other so closely that tidal forces have synchronized their rotation, causing them to always show the same face to their partner, just like the Earth-Moon system, but on a much smaller scale. These cosmic couples tumble through space together, their mutual gravitational embrace strong enough to keep them bound despite the disruptive influences of planetary gravity and solar radiation pressure. The synchronization process takes millions of years to complete, gradually slowing their rotation until they achieve perfect tidal lock. creating stable configurations that can persist for the remainder of the solar system's lifetime. In the depths of interstellar space, there are regions where the density of matter is so low that individual atoms are separated by distances equivalent to several these sparse fields. Yet environments still support complex chemical reactions that proceed over timescales of millions of years. These ultra-dilute laboratories operate according to quantum mechanical principles that become apparent only when matter is spread so thin that individual particles rarely encounter each other. The resulting chemistry produces molecules that would be impossible to create under terrestrial conditions, including exotic compounds that exist only in the coldest, most rarefied regions of the cosmic medium. Certain pulsar systems have been discovered where the neutron star's rotation has become so stable that it serves as a more accurate timekeeper than atomic clocks, maintaining precision that would gain or lose less than a second over millions of years. These stellar chronometers result from the conservation of angular momentum during stellar collapse, concentrating the original star's rotation into an object no larger than a city while preserving its temporal stability across cosmic ages. The radio beams emitted by these pulsars sweep across space with metronomic regularity, creating natural lighthouses that can be detected from thousands of light years away. There are planetary systems where multiple worlds orbit in perfect resonance, their orbital periods related by simple mathematical ratios that create gravitational harmony spanning millions of miles. These cosmic symphonies result from the gradual migration of planets during their formation, with gravitational interactions nudging them into stable configurations where their orbital energies are perfectly balanced. The resulting systems can maintain their resonant structure for billions of years, with each planet's gravity reinforcing the stability of its neighbors in an intricate dance that demonstrates the mathematical beauty underlying celestial mechanics. In certain regions of galaxy clusters, the space between individual galaxies is filled with hot gas that glows faintly in X-ray wavelengths, creating a diffuse medium that connects distant stellar systems in a web of superheated plasma. This intracluster medium contains more mass than all the galaxies within the cluster combined, yet it remains nearly invisible to optical telescopes due to its extreme temperature and low density. The gas serves as a fossil record of ancient galactic collisions and mergers, preserving chemical signatures from stellar explosions that occurred billions of years ago in galaxies that no longer exist as separate entities. Some comets have orbital periods so long that they return to the inner solar system only once every few million years, spending the vast majority of their existence in the cold outer darkness where they remain unchanged by solar heating. These ultra-long period visitors carry pristine samples of the material from which the solar system formed, their surfaces unaltered by the sublimation processes that modify shorter period comets. When they finally make their rare appearances near the Sun, they create spectacular displays as their ancient ices vaporize for the first time in eons, releasing gases and dust that have been frozen in place since the dawn of planetary formation. There are stellar remnants called neutron stars that have become so dense that a teaspoon of their material would weigh more than all the cars on Earth combined. Yet these ultra-compact objects can spin faster than kitchen blenders while maintaining perfect spherical symmetry. The matter within these stellar corpses has been compressed beyond the point where normal atomic structure can exist, creating a form of degenerate matter where neutrons are packed together like balls in a cosmic ball pit. Despite their incredible can density, these objects maintain structural stability for trillions of years, slowly cooling and spinning down while remaining as perfect spheres only 12 miles in diameter. In the vast spaces between galactic clusters, there exist cosmic voids so empty that a journey across one at the speed of light would take hundreds of millions of years without encountering a single galaxy. These cosmic deserts represent the largest structures in the universe, regions where the normal processes of gravitational collapse have failed to concentrate matter into the familiar patterns of stars and galaxies. The few atoms that do exist in these voids drift in near-perfect isolation, experiencing temperatures and pressures that approach the theoretical limits of emptiness, while participating in the universe's grandest architectural features. Some exoplanets have been discovered with such extreme orbital characteristics that they experience seasons lasting decades or centuries, with one hemisphere remaining in darkness for years at a time, while the other basks in continuous sunlight. These worlds follow highly elliptical paths around their stars, creating climate variations far more extreme than anything experienced on Earth. During their closest approach to their parent star, these planets may become hot enough to melt lead, while their most distant orbital phases could freeze the atmosphere into solid layers on the planet's surface. There are magnetic field structures in space that create invisible barriers capable of deflecting charged particles traveling at nearly the speed of light, forming cosmic shields that protect entire regions of the galaxy from harmful radiation. These magnetospheric boundaries result from the interaction between stellar winds and the galactic magnetic field, creating bow shock regions where high-energy particles are reflected back into interstellar space. The resulting protected zones can span dozens of light years, creating cosmic safe havens where more delicate processes like planet formation and biological evolution can proceed without constant bombardment by cosmic rays. In certain binary star systems, the two stellar components have evolved at different rates, creating partnerships where an ancient, evolved star orbits alongside a younger, more active companion. These mismatched pairs result from the complex dynamics of stellar evolution in gravitationally bound systems, where mass transfer and orbital evolution can rejuvenate one star while accelerating the aging of another. The resulting stellar odd couples demonstrate how gravitational relationships can fundamentally alter the life cycles of stars, creating evolutionary pathways that would be impossible for isolated stellar objects. Some asteroids have been discovered with such porous internal structures that they would float if placed in an ocean, despite being made of rock and metal that individually are much denser than water. These cosmic sponges formed through gentle accretion processes, where dust and small particles stuck together without being compressed into solid rock, creating objects that are more empty space than actual matter. The low gravity on these rubble pile asteroids means that walking on their surface would feel more like floating, with each step potentially launching you into a gentle arc that could last for hours before you slowly settle back down. There are regions in the outer solar system where the gravitational influence of Neptune has created a complex resonance structure that traps small objects in stable orbital patterns, forming populations of cosmic prisoners that have been following the same paths for billions of years. These Kuiper Belt objects demonstrate how gravitational mechanics can create order from chaos, organizing the debris of planetary formation into predictable families that reveal the hidden architecture of gravitational force. Some of these trapped populations may contain pristine samples of the material from which the outer planets formed, preserved in their current orbits since the solar system's youth. In certain globular clusters, the gravitational interactions between hundreds of thousands of stars have created core regions where stellar collisions become possible, leading to the formation of exotic objects that cannot exist in less crowded stellar environments. These cosmic city centers experience population densities millions of times greater than the space around our sun, creating conditions where stars can merge, exchange mass, or capture companions through gravitational encounters. The resulting stellar exotica include blue straggler stars that appear younger than their neighbors, and X-ray binary systems where compact objects feed on material stripped from normal stellar companions. Some planetary moons have such eccentric orbits that they experience extreme tidal heating during their closest approach to their parent planet, followed by periods of cooling and solidification as they swing out to greater distances. These thermally cycling worlds undergo regular phases of geological activity that can last for thousands of years, creating surface features that change dramatically over time. The repeated heating and cooling creates complex internal structures where liquid and solid regions coexist, potentially forming subsurface environments that could harbor unique forms of chemistry or even biology adapted to extreme temperature variations. There are stellar wind bubbles created by massive stars that can extend for dozens of light years in all directions, carving out vast cavities in the interstellar medium that persist long after the stars that created them have exploded as supernovae. These cosmic excavations reshape entire regions of the galaxy, creating low-density zones where subsequent generations of star formation proceed under different conditions than in the undisturbed interstellar medium. The hot, tenuous gas within these bubbles can reach temperatures of millions of degrees, yet it remains so thin that it would be considered a perfect vacuum by earthly standards. In certain protoplanetary disks around young stars, astronomers have observed the formation of spiral density waves that transport angular momentum outward, while allowing material to spiral inward toward the central star. These cosmic whirlpools operate according to the same fluid dynamics principles that create spiral arms in galaxies, but on much smaller scales where individual dust grains and gas molecules participate in the flow patterns. The resulting structures help regulate the rate at which new planets can form while creating the complex architecture observed in mature planetary systems. Some white dwarf stars have been discovered with planetary systems that formed after the star's main sequence lifetime ended, creating worlds that orbit the cooling remnant of their original sun while bathed in the faint glow of stellar death. These second-generation planets may have formed from the debris of earlier worlds that were destroyed when their parent star evolved into a red giant, demonstrating how planetary systems can regenerate themselves even after experiencing catastrophic destruction. The resulting environments are unlike anything found around main sequence stars, with stable orbits around objects no larger than Earth, yet containing more mass than our Sun. There are cosmic ray particles that have been accelerated to energies so extreme that when they collide with Earth's atmosphere, they create cascades of secondary particles that can be detected by arrays of sensors spread across thousands of square miles. These ultra-high energy messengers carry information about the most violent processes in the universe, having been accelerated by shock waves from supernova explosions or the magnetic fields around black holes. Despite traveling at nearly the speed of light, some of these particles may have been journeying through space for millions of years before finally encountering our planet, carrying with them the signature of cosmic events that occurred when Earth was a very different world. In certain regions of molecular clouds, the interplay between magnetic fields and gravitational collapse creates filamentary structures that channel material toward the sites where new stars will eventually form. These cosmic highways can extend for dozens of light years, serving as conduits that funnel gas and dust from large volumes of space into the dense cores where stellar ignition becomes possible. The resulting star formation process becomes organized along these magnetic filaments, creating stellar nurseries with structure and order that reflects the invisible architecture of interstellar magnetic fields. Some planetary ring systems have been observed undergoing slow evolution as gravitational perturbations gradually spread ring material over wider orbital ranges, creating expanding structures that will eventually become too diffuse to remain visible. These cosmic time lapses demonstrate how even the most stable-appearing celestial features are temporary on astronomical timescales, with ring systems representing brief moments of organizational beauty in the otherwise chaotic process of small-body orbital dynamics. The particles within these evolving rings continue to follow the laws of celestial mechanics, even as their collective behavior creates patterns that change and dissolve over millions of years. There are asteroid families whose members share not only similar orbital characteristics, but also identical mineral compositions, providing evidence that they originated from the catastrophic breakup of a single large parent body billions of years ago. These scattered siblings continue to follow orbital paths that bear the signature of their common origin, creating groups of objects that serve as natural laboratories for studying the internal structure and composition of ancient planetesimals. By analyzing the different types of material exposed in family members of various sizes, scientists can reconstruct the layered structure of objects that formed during the earliest phases of solar system evolution. In the depths of certain gas giant atmospheres, convection currents transport heat from the planetary interior to the surface with such efficiency that these worlds radiate more energy than they receive from their parent star. These planetary heat engines demonstrate how gravitational potential energy stored during formation can continue to power geological activity for billions of years, creating dynamic atmospheres and magnetic fields that persist long after the initial accretion process has ended. The resulting weather systems can maintain coherent structures for decades or centuries, creating storm systems that dwarf terrestrial hurricanes while following atmospheric dynamics that operate under extreme pressure and temperature conditions. Some binary star systems have orbital periods so short that the two stellar components complete a full revolution around their common center of mass in less time than it takes Earth to rotate once on its axis. These ultra-compact binaries push the limits of how close two stars can orbit without merging, creating gravitational laboratories where the effects of general relativity become apparent in the gradual decay of orbital energy due to gravitational wave emission. The resulting systems serve as natural testing grounds for Einstein's theories, while providing direct evidence for phenomena that were predicted theoretically decades before they could be observed. There are exoplanets that have been discovered in such close proximity to their parent stars that their surfaces remain molten despite being composed of rock and metal, creating worlds where geological processes operate under conditions that turn solid minerals into flowing lava oceans. These ultra-hot planets experience dayside temperatures exceeding those found in some stellar atmospheres, yet they maintain stable orbits and may even possess atmospheres composed of vaporized rock and metal compounds. The extreme conditions on these worlds provide natural laboratories for studying how familiar geological processes behave under temperature and pressure regimes that cannot be reproduced in earthly experiments. In certain regions of the cosmic web, dark matter filaments have become so dense that they focus gravitational lensing effects, creating natural magnifying glasses that allow astronomers to observe galaxies that would otherwise be too distant and faint to detect. These cosmic telescopes result from the precise alignment of dark matter structures with background galaxies, demonstrating how the invisible architecture of the universe can be revealed through its gravitational effects on visible light. The resulting observations provide windows into cosmic epochs that existed when the universe was only a fraction of its current age, carrying information about the formation of the first stellar populations and galactic structures. Some cometary nuclei have been found to contain organic molecules of such complexity that they rival the chemical diversity found in terrestrial biological systems. Yet these compounds formed through purely non-biological processes in the cold depths of space. These cosmic chemistry sets demonstrate how the basic building blocks of life can arise naturally through stellar nucleosynthesis and interstellar chemical reactions, suggesting that the molecular foundation for biology may be distributed throughout the galaxy in vast reservoirs of prebiotic material. When these comet-borne organics are delivered to planetary surfaces through impact events, they provide ready-made chemical starting points for the development of more complex biological processes. There are neutron star systems where the intense gravitational field has become strong enough to bend light rays into closed orbits, creating regions where photons can circle the stellar remnant multiple times before either escaping to infinity or falling past the event horizon. These photon spheres represent the boundary between bound and unbound light trajectories, demonstrating how extreme gravitational fields can trap electromagnetic radiation in the same way that planetary gravity captures orbiting satellites. The resulting optical effects create complex lensing phenomena, where distant objects can appear distorted, magnified, or even multiply imaged when viewed through the gravitational field of these compact stellar remnants. In certain protoplanetary systems, astronomers have observed the formation of planetary embryos that grow through the gradual accretion of smaller objects, creating worlds that increase in size and complexity over millions of years while clearing their orbital paths of debris. These cosmic construction projects demonstrate how the chaotic process of early planetary formation gradually gives way to more organized systems where gravitational dominance creates stable, long-term orbital configurations. The resulting planetary systems often show evidence of their violent formation history in the form of large impact craters, unusual compositions, or orbital characteristics that reflect the stochastic nature of the accretion process. Some stellar associations contain stars with such a wide range of masses that their evolutionary timescales span orders of magnitude, creating stellar communities where the most massive members complete their entire life cycles, while the smallest stars have barely begun their main sequence burning phase. These cosmic generation gaps demonstrate how stellar evolution proceeds at vastly different rates depending on initial mass, with the most massive stars serving as cosmic fireflies that burn brightly and die young, while their low-mass companions settle in for lifetimes that can exceed the current age of the universe. The chemical enrichment provided by successive generations of massive star deaths gradually changes the composition of the interstellar medium, creating conditions that allow later generations of stars to form rocky planets and potentially develop complex chemistry. There are regions in the outer atmospheres of gas giants where atmospheric waves propagate vertically through dozens of pressure scale heights, creating oscillations that can transport energy and momentum from the planet's deep interior to the edge of space. These planetary seismic waves result from convective processes in the planet's core that generate pressure disturbances capable of traveling thousands of miles through increasingly thin atmospheric layers. The resulting wave patterns create temperature and composition variations that can be detected by sensitive spectroscopic observations, providing information about conditions in planetary regions that remain inaccessible to direct measurement. In certain galaxy clusters, the gravitational interactions between member galaxies have created tidal streams and stellar bridges that connect individual systems across distances of millions of light years. These galactic highways form when close encounters strip stars and gas from galaxy peripheries, creating temporary structures that trace out the orbital paths followed during gravitational encounters. The stars within these tidal features continue to shine normally even as they are separated from their parent galaxies, creating spectacular displays of stellar architecture that demonstrate how gravitational forces can reshape cosmic structures on the largest observable scales. Some brown dwarf objects have been discovered with planetary systems of their own, creating miniature solar systems where worlds orbit failed stars that never achieved the mass necessary to sustain nuclear fusion. These substellar planetary systems challenge traditional definitions of what constitutes a star versus a planet, creating orbital configurations where the distinction between primary and secondary objects becomes blurred. The resulting systems may represent the most common type of planetary architecture in the galaxy, since brown dwarfs are thought to be more numerous than conventional stars, while still being capable of retaining gravitationally bound companions. There are cosmic structures called galactic bars that form when gravitational instabilities in disk galaxies create elongated concentrations of stars and gas that rotate more slowly than the surrounding galactic material. These stellar traffic jams can persist for billions of years, funneling material toward galactic centers while creating spiral density waves that propagate outward through the galactic disk. The resulting patterns demonstrate how collective gravitational effects can create large-scale organization in systems containing hundreds of billions of individual stellar components, turning what might otherwise be chaotic stellar motions into coherent, long-lived structural features. In certain regions of space, there are stellar winds so gentle they take millions of years to travel from one star to another, carrying with them microscopic dust grains that serve as seeds for future worlds. These interstellar breezes move with the patience of geological time, transporting the chemical elements forged in stellar cores across vast distances to regions where new planetary systems are just beginning to form. The dust particles within these winds have been polished smooth by their journey through space, creating microscopic spheres of pure elements that will eventually become incorporated into asteroids, comets, and perhaps even the atmospheres of distant worlds. Each grain carries within it the nuclear history of its parent star, preserving the memory of fusion reactions that occurred millions of years ago in stellar furnaces that may no longer exist. Some planetary systems have been discovered where the gravitational influence of a distant stellar companion creates orbital resonances so complex that planets follow paths that trace out perfect geometric patterns when viewed over thousands of years. These cosmic mandalas result from the delicate balance between multiple gravitational influences, creating stable configurations where each world's motion reinforces the stability of its neighbors in an intricate dance of celestial mechanics. The resulting orbital architectures can persist for billions of years, with planets maintaining their resonant relationships even as stellar evolution gradually changes the mass and luminosity of their parent stars. These systems demonstrate how mathematical beauty can emerge naturally from the fundamental forces that govern motion in space. There are molecular clouds in space where the temperature is so uniform that thermal gradients spanning light years differ by less than a single degree, creating regions of almost perfect thermal equilibrium that serve as natural laboratories for studying quantum effects on astronomical scales. Within these cosmic refrigerators, chemical reactions proceed with glacial slowness, allowing complex molecules to form through pathways that will be impossible under more energetic conditions. The resulting chemistry produces compounds of stunning intricacy, including molecular structures that exist nowhere else in the universe, except in these cold, patient environments where time moves differently and matter behaves according to quantum rules that become apparent only in the absence of thermal choke. In certain binary asteroid systems, the two components have become so perfectly tidally locked that they present the same face to each other throughout their orbital dance, creating gravitational partnerships where each world experiences permanent day and night hemispheres, determined not by rotation, but by their companion's presence. These cosmic couples tumble through space together in synchronous rotation, their surfaces sculpted by millions of years of tidal heating and cooling that has created unique geological features unlike anything found on solitary worlds. The gravitational embrace between these paired asteroids is so precise that they maintain their separation to within a few meters over orbital periods that can last for days or weeks, demonstrating how even small objects can achieve remarkable gravitational stability when their dynamics reach equilibrium. Some white dwarf stars have cooling histories so precisely determined that they serve as cosmic chronometers, their surface temperatures providing direct measurements of how long they have been cooling since their formation billions of years ago. These stellar time capsules preserve information about conditions in the early galaxy, when the first generations of stars were completing their evolution and scattering heavy elements into space. As they continue their slow fade from white-hot to red to invisible black, these cooling remnants carry with them the thermal memory of stellar death, providing astronomers with direct evidence for the age and evolution of galactic stellar populations. Their patient cooling process will continue for trillions of years, long after all conventional stars have exhausted their nuclear fuel and the galaxy has entered its final stellar graveyard phase. There are cosmic ray particles that have been bouncing between magnetic field boundaries for so long that they have circumnavigated the entire galaxy multiple times, while gradually gaining energy from each magnetic encounter. These well-traveled messengers carry information about magnetic field structures spanning thousands of light years, having experienced the full electromagnetic architecture of galactic space during their extended journey. Some of these particles may have originated from supernova explosions that occurred when the solar system was in a completely different part of its galactic orbit, making them cosmic veterans that have witnessed the changing face of interstellar space over millions of years of continuous travel. In certain protoplanetary disks, the process of planet formation creates spiral density waves that propagate outward from the sites of planetary growth, carrying away the angular momentum that allows material to continue falling inward toward the central star. These cosmic whirlpools operate according to fluid dynamics principles that create self-organizing patterns in the disk material, with each forming planet generating its own wake of disturbed gas and dust that influences the formation of neighboring worlds. The resulting planetary systems often show evidence of this early dynamical evolution in the form of orbital spacings and eccentricities that reflect the complex interactions between growing planets and their birth environment. Some neutron stars have magnetic field geometries so complex that their radio emission creates lighthouse beams that sweep across space in intricate patterns, producing pulse sequences that change subtly over years or decades as the magnetic field slowly evolves. These stellar timekeepers maintain their rotational stability with such precision that astronomers can detect variations in their pulse arrival times that amount to less than a microsecond over periods of many years. The resulting measurements provide insights into the internal structure of neutron star material, where matter exists in forms that cannot be reproduced in any terrestrial laboratory. Compressed to densities where normal atomic structure breaks down completely, there are regions of the cosmic web where dark matter streams from different directions converge and interact, creating gravitational focusing effects that concentrate both dark and ordinary matter into filaments that can extend across hundreds of millions of light years. These cosmic superhighways serve as conduits for the large-scale flow of matter throughout the universe, channeling material from low-density voids toward high-density regions where galaxy clusters eventually form. The intersection points of these dark matter streams become the sites of the most massive structures in the universe, where thousands of galaxies can be found clustered together in gravitational communities that span distances larger than the local group of galaxies that includes our own Milky Way. In certain stellar nurseries, the magnetic fields threading through molecular clouds have become so tangled and twisted that they create three-dimensional knots of magnetic force that can persist for millions of years while gradually untangling through magnetic reconnection events. These invisible sculptures guide the flow of ionized gas within the cloud, creating preferred directions for material transport that influence where and how new stars will eventually form. The magnetic field patterns can become so complex that they resemble abstract artwork on scales spanning dozens of light years, with field lines that loop, spiral, and braid together in configurations that demonstrate the hidden beauty of electromagnetic forces operating in cosmic environments. Some exoplanets have atmospheric compositions so exotic that their weather systems operate according to chemistry that has no terrestrial equivalent, with clouds made of liquid metals and precipitation consisting of gemstone particles that rain down from skies heated to temperatures exceeding those found in blast furnaces. These alien meteorological systems create climate patterns that can persist for centuries, with storm systems that dwarf terrestrial hurricanes while operating under pressure and temperature conditions that transform familiar materials into states of matter that exist nowhere else in the solar system. The resulting atmospheric dynamics create spectral signatures that can be detected from thousands of light years away, providing remote sensing data about chemical processes occurring on worlds that will never be visited by human explorers. There are asteroid populations whose orbital characteristics preserve detailed information about the gravitational environment that existed during the early phases of planetary formation, when the growing planets were migrating through the solar system and reshaping the architecture of small body orbits. These cosmic archaeological records show evidence of close encounters with planetary embryos that no longer exist, having been incorporated into larger worlds or ejected from the solar system entirely during the chaotic period of heavy bombardment. The surviving asteroids carry within their orbital elements the gravitational fingerprints of these vanished objects, providing clues about how the solar system's current configuration emerged from the primordial chaos of planetary accretion. In certain globular clusters, the stellar population has become so well mixed through billions of years of gravitational encounters that stars originally formed in different regions of the cluster now share nearly identical chemical compositions. This cosmic homogenization process demonstrates how gravitational dynamics can create chemical uniformity on scales spanning dozens of light-years, with stellar atmospheres serving as natural sampling devices that preserve information about the average composition of their stellar community. The resulting chemical signatures provide insights into the formation conditions of these ancient stellar systems, which may represent some of the oldest surviving structures in the galaxy. Some planetary moons have internal structures so complex that they support multiple zones of geological activity, with liquid water oceans sandwiched between layers of different types of ice that form under the extreme pressures found in deep subsurface environments. These cosmic layer cakes demonstrate how gravitational and thermal forces can create stable stratified systems that persist for billions of years, with each layer maintaining its own physical and chemical characteristics, while participating in a larger system of material exchange and energy transport. The boundaries between these layers may serve as interfaces where unique chemical reactions can occur, potentially creating environments that combine the stability of solid phases with the dynamic chemistry possible in liquid systems, TEMS. There are stellar associations where the most massive members have evolved through their entire life cycles and exploded as supernovae, leaving behind neutron stars and black holes that continue to orbit within the gravitational potential of the original stellar group. These cosmic graveyards preserve the memory of stellar communities that once blazed with the light of dozens of massive blue giants, now reduced to invisible compact objects that interact only through their gravitational influence on the remaining low-mass stars. The supernova explosions that created these stellar remnants also enriched the local interstellar medium with heavy elements, creating chemical conditions that allowed subsequent generations of star formation to produce planets capable of supporting complex chemistry and potentially even biological processes. In certain regions of galaxy clusters, the hot intracluster gas has been heated to temperatures so extreme that it emits X-rays with energies comparable to those produced in particle accelerators, creating natural high-energy physics laboratories spanning millions of light-years. This superheated plasma contains more mass than all the galaxies in the cluster combined, yet it remains so diffuse that it would be considered a perfect vacuum by terrestrial standards. The gas serves as a fossil record of the violent merger events that assembled the cluster over billions of years, preserving chemical signatures from stellar explosions and galactic collisions that occurred when the universe was much younger and more chaotic than it appears today. Some binary star systems have evolved into configurations where one component has become a white dwarf, while its companion remains on the main sequence, creating stellar partnerships where the evolutionary clock has stopped for one member, while continuing to tick for the other. These mismatched pairs demonstrate how stellar evolution can proceed at vastly different rates, even for stars that formed from the same molecular cloud and began their lives with nearly identical properties. The gravitational interaction between the evolved and unevolved components can lead to complex mass transfer processes that rejuvenate the white dwarf while gradually stripping material from its companion, creating dynamic systems that continue to evolve long after one star has officially died. There are cosmic structures called bow shocks that form when stars move through the interstellar medium at speeds exceeding the local sound speed, creating compression waves in the surrounding gas that can extend for light years in all directions. These stellar wake patterns demonstrate how even individual stars can influence their galactic environment, pushing aside interstellar material and creating cavities of low-density gas that persist long after the star has moved on to other regions of the galaxy. The shocked gas in these bow waves often glows faintly in infrared wavelengths, creating beautiful curved structures that trace out the path of stellar motion through space, while revealing the otherwise invisible medium between the stars. In certain protoplanetary systems, the gravitational influence of forming gas giants creates gaps in the surrounding disk material, carving out channels that can extend across billions of miles while remaining stable for millions of years. These cosmic moats demonstrate how planetary formation is a self-regulating process, with growing worlds clearing their orbital neighborhoods of debris while simultaneously accreting material at rates determined by the balance between gravitational attraction and orbital dynamics. The resulting disk structures often show complex patterns of rings and gaps that reflect the gravitational architecture of the developing planetary system, providing astronomers with direct observational evidence for how worlds like those in our own solar system come into existence. And now, as we drift toward the end of our cosmic journey, let your thoughts grow as soft as the ancient light that has traveled billions of years just to reach your eyes tonight. We've wandered together through stellar nurseries and diamond rain, past tidally locked worlds bathed in eternal twilight and neutron stars that spin faster than thought itself. We've felt the gentle pull of dark matter rivers and listened to the quiet songs that pulsars sing across the void. In all of this vastness, in all of these impossible scales and unimaginable phenomena, there's something deeply comforting about the universe's patience. Stars take millions of years to be born. Galaxies dance together across billions of years, and even light itself travels for eons just to tell us stories of distant worlds. Everything moves with such gentle deliberation, such cosmic calm. As you settle into sleep tonight, remember that you're floating on a small blue world that's part of something infinitely larger and more beautiful than we can fully comprehend. The same forces that shape galaxies also shape your dreams, and the same elements forged in ancient stellar furnaces now flow quietly through your veins. Thank you for drifting through the cosmos with me tonight. May your dreams be filled with starlight and the peaceful rhythms of a universe that never stops creating wonder. One gentle breath at a time. Sleep well.